Hi everyone, I'm Dr. Hafizal Yahya. Welcome to SMJP 1022 Experimental Method. In this session, we are starting with Chapter 1, Measurement, Standard and Units. In this part of the chapter, and we will be focusing on measurement and standard. This part, we will start with 1.1 until 1.4, which is Introduction to Measurement, Engineering Measurement, Evolution of Measurement Tools, and finally, Standard of Measurement. Nowadays, there is an increasing demand for measurement and control of a physical variable in many applications, whether in engineering, science, or industry. This demand is also supported by continuous advancement in instrumentation techniques. Now, let's look at the two key concepts here. First, instrumentation. This refers to the tools or device we use to perform measurement, such as sensors, gauges, or even simpler tools like rulers. Second, measurement. This is simply the act of determining the size or quantity of the something. For example, when we use a ruler to measure the length of a piece of paper, that's measurement. Essentially, measurement is always a comparison of a quantity with a standard reference. Past engineers often design systems to trial and error, which sometimes cause serious losses in both life and costs. Today, we use a modern approach by combining theory with experiments to create reliable models and ensure precise measurement. As engineers, we are expected to design good experiments, estimate accuracy, interpret results carefully, and understand the limitation of our data. Most importantly, we must verify that our findings are supported by real experiment evidence. In mass production, precision measurement is absolutely essential. Every single part of a product must be made to exact standards so that all parts are intangible, meaning they can fit together perfectly, no matter when or where they are produced. This level of interchangeability is only possible through two things. First, improve methods of measurement, and second, the use of mechanically powered machines to produce consistent results. To maintain quality, we must also rely on accurate measuring equipment. This allows us to control and ensure uniformity at every step, starting from the blueprints, design, all the way to the finished assembly. To ensure lasting dependability in engineering and manufacturing, we must start with accurate measuring tools. These tools need to be produced from high-quality materials, carefully manufactured, and most importantly, rigidly inspected to guarantee reliability. Accurate tools help us achieve near perfection, ensuring products meet specification and reducing defective parts. This is cost-effective and guarantees customer satisfaction by delivering consistent quality and efficiency. In the earliest time, people already need to measure things, since there were no standard tools. They used parts of the body, like an inch from the thumb, a handspan, a foot, or a cubit, to estimate dimension. Back then, high accuracy wasn't important because most products were handmade and custom-made. Today, we have modern measuring tools such as steel ruler, caliper, and micrometers. We also use electronic devices combined with computer technology to achieve much greater accuracy and consistency. Developed, there was a growing need for a common measurement standards. This standard had to be recognized internationally and fixed so that measurement would be consistent across countries. Every nation has own body responsible for maintaining this standard. In Malaysia, it's SIRIM, the Standard and Industrial Research Institute of Malaysia. In the United States, it's NIST, the National Institute of Standards and Technology. And in the UK, it's BSI, the British Standard Institution. Standard of length. The definition of a meter has changed over time to become more accurate. In the 18th century, it was first introduced in France and defined as 1/10 millionth of the distance from the equator to the North Pole. In the 19th century, a platinum iridium bar was made as the international meter standard. In the 20th century, the meter was redefined using the wavelength of Krypton's 86 light. Today, standard of mass. The definition of a kilogram has also changed over time to improve accuracy. In the 18th century, France introduced the kilogram, defined as a mass of 1 liter of pure water at 4 degrees Celsius. In the 19th century, an international prototype kilogram, a platinum iridium cylinder, was made and kept in Paris as a world standard. During the 20th century, the same prototype was still used, but scientists discovered that its mass change slightly over time. In the modern era, since 2019, the kilogram has been redefined using Planck constant, making it no longer dependent on any physical objects. That gives us a definition that is precise, stable, and universal. Standard of time. The way we measure time has become more precise over the years. In the 19th century, Greenwich Mean Time, or GMT, was adopted. It was based on the Earth's rotation and the prime meridian. In the 20th century, quartz clocks were introduced. They measured time using the vibration of quartz crystals, giving much better accuracy. By the mid-20th century, the first atomic clock was developed using vibration of cesium-133 atoms. And since 1967, the SI second has been defined as exactly 9 billion vibrations of cesium-133. This is our current precise and universal standard of time. Standard of temperature. The temperature scale has evolved over time to become more accurate and universal. In the 18th century, two important scales were introduced. The Fahrenheit scale in 1714, based on the freezing of brine and human body temperature, and the Celsius scale in 1742, where 0 degrees is the freezing point of water and 100 degrees is the boiling point. In the 19th centuries, the Kelvin scale was proposed, starting at absolute zero, the foundation of thermodynamics. By the 20th century, the triple points of water at 273.16 Kelvin was used as a temperature reference. In the modern era, since 2019, the Kelvin has been redefined using the Boltzmann constant, making it independent of any material reference and universal precise. There are four common temperature scales: Celsius, Fahrenheit, Kelvin, and Rankine. The relationship between these scales can be used with a few key equations as shown in this formula below. This formula allows us convert between different temperature units accurately in engineering and scientific calculation. This is the end of part 1. I will see you in the next parts 2, units and measurement.